Hello everyone, our group will be presenting Stack Overflow attack. A stack overflow is a buffer overflow error that occurs when a computer program attempts to use more memory space in the call stack that was allocated to it. The call stack, also known as the stack segment, is a fixed size buffer that stores local function, variable, and return address data as the program runs. The call stack uses a last in, first out memory architecture. Each function is assigned its own stack frame for storing variables and address data. When a function is called, its stack frame is pushed to the top of the call stack. The stack frame will be kept in memory until the function is finished executing. The stack frame is then removed from the stack, freeing up memory for the later stack frame. The size of the call stack is typically set at the beginning of the program. Its size is determined by a variety of factors, including the host computer's architecture, the programming language used, and the amount of memory available in the system. A stack overflow occurs when a program requires more memory than is available in the call stack, causing the program to crash. Next, we will look into what happens during the process. When a stack overflow occurs, excess data can override critical memory such as variable values and return addresses. This can disturb program execution. In some cases, the program crashes immediately, and in other cases, program continues on running, making it difficult to detect and troubleshoot. Program prone to stack overflow can expose security risk. Hacker can exploit these vulnerabilities by overriding the call stack, allowing them to inject their own executable code. For example, hacker may alert sensitive data. For example, they can change the password, they can delete the files, or gain the unauthorized access to the system.
Key vulnerabilities in Stack Overflow attacks. Number 1 is lack of input size validation. So the risk is an attacker can input more data than the buffer can handle, causing a buffer overflow. 2 is unsafe functions. So the vulnerability is using unsafe functions that don't limit input size. And the risk is attackers can overwrite the stack, including function return addresses, leading to code execution. Number 3 is unprotected stack frames. The vulnerability is stacks frames that store return addresses and local variables are susceptible to being overwritten. The risk is overwriting the return address can redirect execution to attacker-controlled code, enabling arbitrary code execution. Examples: attackers can inject malicious shellcode and overwrite the return address to execute it. Number 4 is absence of modern security mechanisms. So the vulnerability is lack of protections like stack canaries, DEP, which is data execution prevention, or address space layout randomization. The risk is without these protections, stack overflows can be exploited more easily. An example is older systems or insecure applications may allow code executions without these defenses. And the key point is Stack Overflow vulnerabilities occur when unsafe memory handling allows attackers to overwrite memory areas like return addresses. Exploits can lead to control flow hijacking or arbitrary code execution.
Causes and consequences. In the context of an attack, the overflow can be used to control code execution, allowing the attacker to potentially do anything they want. This happens due to the return address being overwritten through the buffer overflow. The return address represents the location and code the program executes after it is done with the current function. The return address can be manipulated to execute whatever code the attacker desires. So right after the code, right after like a stack or an array, there's a return address, and then that return address can be manipulated through buffer overflow to either send it to a different function or have the code in the stack or array in itself, and it will execute it right through there. Causes and consequences. Most causes of stack overflow is poor user input validation. Most programming languages have a bound error checking, such as like Python. However, some languages like C and C++ do not have a bound error checking to optimize program speed. Some other causes for stack overflow are the following: recursive functions without a proper base case, use of unsafe functions, lack of bounds checking, and this can lead to many unwanted consequences such as DOS, which is denial of service, data corruption and system instability.
The Morris worm, created by Robert Tappan Morris, became the first major internet worm, marking a turning point in cybersecurity. It exploited a stack buffer overflow vulnerability in Unix systems' finger daemon. This allowed the worm to inject code into the stack and execute it remotely, spreading itself across other vulnerable systems. The impact was substantial. It infected around 6,000 computers, which was about 10% of the internet at the time. The worm caused severe slowdowns, making systems almost unusable and leading to millions of dollars in recovery costs. The Morris worm highlighted critical lessons for cybersecurity, particularly the importance of input validation and secure coding practices. By validating inputs and avoiding unsafe functions, developers can prevent similar vulnerabilities, protecting systems from buffer overflows and other attacks.
How to detect and prevent stack overflow. To detect and prevent stack overflow, there are a few techniques and strategies to keep in mind. For detection, you can look out for runtime errors, especially in languages that automatically handle stack overflows. Debugging tools are really useful for tracing the stack and pinpointing problems like excessive recursion. You can also use memory monitoring tools to keep an eye on stack usage and catch any potential issues early. For prevention, one key step is to limit how deep recursion can go, either by setting a maximum depth or switching to iteration if recursion starts getting too deep. Another helpful strategy is optimizing recursive functions, like using tail recursion when possible to keep stack growth in check. In some cases, you might be able to increase the stack size, but this should really be a last resort. Lastly, it's important to have good error handling in place so you can catch potential overflows before they become a problem.